Hello everyone, welcome to lecture 18 of the course Applied Seismology for Engineers. Myself Dr. Abhishek Kumar. In previous lectures, starting with lecture 14, 15, 16, we discussed about different kinds of seismic waves which are generated from the source and reaching to the recording station. At the same time, if recording station is not there, building is there, then these seismic waves will interact with the structures, and depending upon the resistance structure is going to offer to the loading induced by seismic waves, will decide whether the structure or any particular kind of soil or any other structure, whether it will be able to withstand the additional loading because of seismic activity or not. Then we discussed the Guwahati equations which are going to control the primary wave propagation through a particular medium. In such a case, the particle will undergo to and fro motion in the direction of wave propagation. Then we determined what will be the Guwahati equation of motion for primary wave. Followed by that, we discuss about what if secondary wave, that is the wave which is followed by a primary wave or reaching second at the recording station, is propagating through a particular medium. What will be the Guwahati equation? We discussed when these two waves, primary wave is propagating, it is causing to and fro motion. When shear wave is moving through a particular medium, it is going to trigger shearing in the direction perpendicular to the wave propagation. That means, both in upward and downward direction as well as in horizontal direction. Both these direction will be perpendicular to the direction of wave propagation. Continued with that particular discussion, we try to determine the Guwahati equation of motion, and then in lecture 17 we discuss about how this particular Guwahati equation of motion can be solved using method of variable separable, because there will be component of displacement which is a function of space, there is a component of displacement which is a function of time. So, when we take both these components into account, we cannot bifurcate and get one solution. We have to separate function with respect to space, function with respect to time, and then try solving the equation. So, both component will be now used to find out how a particular layer is going to respond if it is subjected to bedrock motion. In lecture 17, we also discussed about whenever there is an incident wave. Firstly, we discussed about local side effect, which is primarily the modification in the ground motion characteristics at a site of interest, primarily because of the local soil characteristics which are available above the bedrock and below the ground surface. At times there can be one layer, at times there can be more than one layer. So, depending upon the stiffness properties of these layers, when we say about stiffness, primarily we are talking about dynamic soil properties, that is damping ratio as well as the shear modulus of the material. When we are talking about the soil, the dynamic properties means these two properties, that is shear modulus as well as damping ratio. It changes with respect to the level of shear strain which a particular earthquake loading is going to induce in the medium of propagation. What it means, if there is a layer of medium, that is soil layer is there, depending upon the shear strain which is mobilized in this particular layer because of propagation of shear wave through this particular medium, that is going to define how much resistance this particular soil layer is going to offer, whether in terms of modulus, shear modulus, whether in terms of damping, and collectively it is going to define how this particular soil layer having one value of damping as well as shear modulus is going to respond to external loading condition. It has been observed number of times across different earthquakes and in different parts of the globe that same site can show very high shear modulus, very low damping ratio, or very low damping ratio, very high shear modulus, depending upon what is the level of shear strain which has been mobilized in that particular soil layer during a particular earthquake loading. In lecture 17, we also discussed that equally with respect to soil characteristics, it is also important to know that the ground motion which has been given to a particular analysis, whether that motion has been defined at bedrock level, that means the rock level which is beneath the soil layers, or it has been defined as outcrop level, that means where the soil is where the rock is exposed to the ground surface, or whether it is bedrock outcrop motion where bedrock is there, but there is no soil above it. So, even that particular bedrock is corresponding to free surface condition. Or another case can arise where the ground motion which is been recorded and provided for ground response analysis, that motion itself is available at the ground surface, that means where one is going to construct a particular building or any other utility. So, depending upon where the motion has been recorded, one should be careful in taking whether the particular motion, ground motion signature can be directly taken into account for doing ground response analysis, or the motion which has been provided, whether it is corresponding to regional records, whether it is synthetically generated motion or motion adopted from other region having similar seismic activity as that of the site of interest. Once a motion has been selected, because it is how the soil layers are going to respond to that particular motion. So, one is the input soil properties which one can determine based on in situ investigation as well as quantification of dynamic soil properties of soil. Input motion, if it is bedrock motion, you can directly use. If it is bedrock outcrop motion, you have to suitably modify that particular motion. Similarly, if it is outcrop motion, you have to transfer that motion to bedrock condition. If it is free surface motion, either you can use it directly for quantification of seismic loading, or if it has been recorded at different site, then you have to transfer that motion to bedrock and then use that motion to other site as the same bedrock motion followed by ground response analysis. So, this process of selecting the motion, doing ground response analysis, transferring the motion from bedrock to the surface, transferring motion from surface to bedrock, transferring motion from outcrop to bedrock, or transferring motion from bedrock outcrop to outcrop depends upon the motion, site characteristics and what is the objective, whether it is ground response analysis or determination of bedrock level ground motion characteristics. So, depending upon the objectives, the use of motion and the purpose of ground response analysis can be selected. Then we discussed primarily the motion can be of elastic half space or rigid half space. That means that the motion when it is incidented on the bedrock medium, depending upon the characteristics of the medium, sometimes some portion of seismic energy which the wave is carrying will be contained in that medium and not the entire part of energy will be propagated further upward towards the surface. That will be the part of elastic half space. If it is rigid half space, a significant portion of the energy, or you can say almost all the energy which seismic wave at the time of incident on the bedrock level will be transferred to the surface, and subsequently it will control the response of the soil which is available above bedrock to the different soil layers. So, continuing with that part, now we have understood based on our understanding so far that firstly is the input motion, secondly the bedrock characteristics, thirdly the soil characteristics. Primarily these are the three important informations which one will be interested to know before starting ground response analysis. So, lecture 17 was part 1 of the topic local site effect and ground response analysis. This is continuation of the same topic. Here we will try to solve one typical field problem. So, we will also discuss how to go about the solution. If we recollect the discussion from lecture 17, we will try to remember that at the time of developing the solution for one dimensional ground response analysis, that too based on linear approach, we have to have one is transfer function, second is Fourier spectra of input motion. So, Fourier spectra of input motion means whenever a motion is given to you, generally because of earthquake motion, it will be random in nature. So, when we say Fourier spectra of a given earthquake induced motion, we are interested to find out how many cycles of harmonic motions are present in that particular given motion. Harmonic cycles means the operating frequency of the motion as well as the amplitude of each harmonic motion is going to remain constant. So, when we say we are interested to find out the frequency content of the motion, we are interested to find out that for a given earthquake induced motion, how many samples of harmonic frequency motions are existing. So, that will be on x axis, you can say that is the frequency content of all harmonic motions. Suppose if your ground motion is having n number of harmonic motions, so corresponding to each of those harmonic motion there will be some operating frequency, that is the value mentioned on x axis. Now, being harmonic motion, one is operating frequency, second one is the amplitude at which the motion is operating. So, we can again take into account if this is harmonic motion which is getting repeated cycle after cycle. So, you can see from here what is the operating frequency, and from here we can also find out how much is the amplitude. So, this is the amplitude of the motion, and based on the time taken by wave in each cycle, this is one half cycle, this is another half cycle. So, how much time it has taken, from which you can find out what is the frequency in which one oscillation the motion is completing, that is going to give you how much is the operating frequency, or you can find out from here the time duration, and 1 by time duration you can find out how much is the frequency of this particular harmonic motion. So, here you can take the frequency value f1, and then corresponding to f1 this is the amplitude of the motion, that is a1. So, next time when we see Fourier spectra of any particular ground motion, basically it is going to give you combined information or the summary of all harmonic motions which are present in the motion, and corresponding to each point you will be having some plot like this. So, if you take any particular motion, this is the frequency content of harmonic motion which is present in this particular random motion, and corresponding to this is the amplitude of that motion. So, based on Fourier spectra or Fourier analysis, you can find out how many frequency content of harmonic motions or how many harmonic motions with different operating frequencies are existing in a ground motion. If we recollect the topic where we discussed about the ground motion characteristics, primarily we were looking about three characteristics. One is the duration of the motion, again duration, significant duration, bracketed duration we can take into account, frequency content, again natural frequency is there or predominant frequency is there. Similarly, the amplitude of the motion, again depending upon what is the period of interest, you can go with displacement, velocity or acceleration values. So, here when we say about Fourier spectra, we are basically interested to find out the frequency content of your motion. This motion is, remember, this is the complete Fourier spectra. So, you can write also over here Fourier spectra. So, it is going to give me a complete picture of how many harmonic motions are present in your motion. This is a motion which if I am going to use for ground response analysis, based on the discussion given in lecture 17, this motion which was again, if you remember, this was the motion which was actually given to you, some random motion generated during a particular earthquake, which is basically the response of your point of observation with respect to time. So, you can see with respect to time how the position of this motion is changing, whether it is in terms of acceleration or velocity or displacement values. So, this is the input motion, and from where you had tried determining the frequency content of the motion. So, remember this is the motion which we are taking into account to perform ground response analysis. When we are talking about motion over here in terms of variation with respect to time, we generally refer to as in time domain. When we are taking specifically towards the frequency content of the motion as given in terms of Fourier spectra, we often refer to the term in frequency domain. So, dealing with the ground motions or performing ground response analysis, often we will talk about two terms, one is time domain, other one is frequency domain. So, in this particular lecture, lecture 18, we will be discussing further about ground response analysis. So, topics which were covered in previous class that I have already spoken about: introduction, significance of why ground response analysis is significant, that was discussed in lecture 17, with the citation of different earthquakes and induced damages, which were primarily not confined to only epicentral distance, but even at larger distances. That subsequently gave an indication about the importance of going for site specific ground response analysis. Then we discussed what is local site effect and method based on which one can quantify local site effect, starting with empirical methods, semi empirical methods, theoretical methods, hybrid methods. So, all these we had already had an understanding in a very brief. Further, we discussed more about theoretical methods or numerical method which can be used to quantify local side effect, which take into account the equation of motion as well as the characteristics of input motion. We also discussed that primarily a particular medium will offer resistance in terms of stiffness value, or you can say in terms of shear modulus, because we will be talking about elastic material as well as the damping ratio, which was indicated by D. So, these are the two properties of the medium based on which the material will offer resistance to loading, to deformation when external loading is applied to the particular material. Transfer function, when we talk about transfer function, so that means transfer function was a correlation or the filter which based on which one can quantify how much modification in the ground motion characteristics will happen between the base of that particular layer and the top of that particular layer. So, if that means if there are more than one layer, every time you try determining the transfer function in order to find out how much change in the ground motion characteristics between the bottom of that particular layer and the top of that particular soil layer is happening. Then we discuss about in the light of one dimensional equation of motion, which was given at the end of the solution of shear wave propagating through a particular medium, that was redefined in terms of exponential form. So, now we will be talking about homogeneous undamped soil. When we say homogeneous, so now onward when we will be discussing about ground response analysis, we will be focusing primarily on two things. One is what is the characteristics of the medium which you will be using to quantify local side effect. Medium means soil medium, and secondly, what is the characteristics of the rock medium. Rock medium is the medium on which incident wave is there. So, we will be talking about what is the soil medium and what is the rock medium. As discussed earlier, rigid means whatever incident energy is there, that will be progressing further towards the surface. If it is elastic, some portion of energy will contain there or propagating downward, and rest of the energy or significant portion of the energy will be propagating upward. Now, again in soil, as we discussed, it is going to offer resistance in terms of shear modulus as well as damping ratio, referring to the example of KV solids given in lecture 17. So, here we will be talking about undamped soil, that means we will be taking relatively easier example to understand how to solve a particular equation whether the damping is there or it is not there. So, first is homogeneous soil. I am not taking into account that there is change in the properties of the medium within one particular soil layer, the material properties are not changing. It is undamped system, that means there is no damping associated with the system. Thirdly, the material is associated or the input motion has been transferred from propagation path to rigid rock. Now, let us see with that. This is the general nomenclature and geometry of the problem. So, it is you are having, this is the soil layer in which you are interested to find out how much alteration in the medium characteristic will take place because of this particular soil layer, which is called as undamped. So, soil is undamped, which has been defined by the user or in the beginning of this particular discussion, and the energy or the waves which were propagating through the site are basically to the rigid rock. So, rock medium is rigid, whatever incident energy is there, component of that will be propagated towards movement of the soil layer. Now, if we recollect the equation of motion for right now we are discussing about uniform layer of isotropic linear elastic soil. So, if you remember the discussion with respect to KB solid, the material is undamped. So, the only resistance the material is going to offer to external loading will be in terms of linear elastic spring. That means, corresponding to the loading, the material is only going to offer stiffness, which is going to define how much will be the resistance or modification in the soil properties. Now, this was the equation of motion. That means, the equation which we derive at the end of one dimensional equation of motion related solution, that has been reconverted in terms of A exponential iota omega t plus k z. Z I have used here as the thickness of this particular soil layer, which is given over here. So, this is the value of h is the value of thickness and z is measured in the direction towards the thickness. That means, at any point from z equals to 0 means at the ground surface, and as you move downward, that means you are increasing the value of z, and the value of z can maximum reach up to h, that means the bottom of that particular soil layer. And this equation is going to define how much is the oscillation or how much shearing corresponding displacement happening in the direction of u in the soil medium when it is subjected to vertically propagating SH waves that we have discussed in lecture 17. So, this is vertically propagating SH wave, which is going to induce shearing in horizontal direction in both the directions. So, if wave is propagating like this, shearing will be happening in this direction as well as in this direction, and this is the stratification in the soil layer. And in our ground response analysis, there is an assumption that the soil layer is extending infinitely and is horizontal. So, with that information in the background, u is defined as u, the displacement value, which is a function of space as well as time, is defined as a and b are the value of the coefficients exponential iota omega t plus k z. So, remember this is the thickness of the medium, z is the thickness of the medium, k is wave number, that means how many number of cycles in unit length are going to get completed, that will be defined by wave number k. Omega is operating frequency of external loading condition. So, if you take any harmonic motion, operating frequency of that motion in terms of radians per second. So, you can define the value of omega in generally in circular frequency, and then so all these terms are there. Now, the first term, that is A exponential iota omega t plus kx or kz, it is basically giving you the displacement component which is coming from vertically upward propagating. Secondly, second component is there because there will be redistribution of energy continuously. So, again B exponential iota omega t minus kx, it is basically going to give you the component of displacement because of downward propagating waves from here. So, this particular equation u z comma t, that means the displacement values in horizontal direction varying with respect to space and time is a function of two component. One component is coming because of vertically upward propagating wave, second component is coming from vertically downward propagating wave, and these two are coming because of operating frequency of the motion as well as there is stiffness on the medium. So, if you remember the value of k, that will be again equals to omega over Vs. So, this is the value of wave number k, omega over Vs. So, omega is operating frequency and Vs is going to define how much is the stiffness in the medium. Collectively based on this equation, you can define in unit length how many complete number of cycles of given motion can be completed, that will be defined by wave number. Okay, so, continuing with this particular discussion, this is the equation of motion, general equation of motion. Only thing, if we clearly observe this particular equation, we will see that the value of k is a function of stiffness of the medium, which is an indication of linear elastic soil. That means, we are only taking into account that the correlation between shear stress and shear strain is uniform throughout the loading, or in other words, shear stress and shear strain are directly proportional to each other, and the constant of proportionality is called as shear modulus. That means, the value of tau equals g times gamma, that is shear strain. So, this is solely governing the shear stress mobilized due to external loading condition in the medium of interest. Referring to the problem definition, again we are talking about an undamped system. So, you see over here, if we can recollect KV solids, some component of stress was coming from shear modulus, some component of stress was coming from damping or damper. But here in this particular case, it is only the elastic spring which is going to offer resistance or mobilizing the stresses in a particular medium, which is given in terms of elastic spring or the value of shear modulus. So, one thing is clear, we are talking about linear elastic spring where the only resistance from shear modulus. Secondly, k value is given over here, it is only a function of shear modulus or shear wave velocity. However, if you take both parameter, that is shear modulus as well as damping ratio into account, you will have additional component over here, and that particular time this particular wave number will also become complex wave number. That means, if we take into account rather than undamped system, if we take into account damped system, that means now the resistance the medium is going to offer will have additional component which is a function of damping ratio, which is not applicable in this particular case. So, I am going to cut it here, but that is how you can distinguish between one type of medium of interest to other type of medium of interest. So, when undamped system as mentioned over here is available, you have this as the governing equation of motion. When system become damped, the k value will be replaced by complex wave number. Similarly, if the medium subjected to or the incident wave are applied at elastic half space, again there will be some damping in the bedrock medium itself. So, again the governing equation corresponding to rigid bedrock condition will also be modified, taking the damping characteristics of bedrock medium into the solution. So, this was the equation u z comma t equals to a exponential iota omega t plus k z plus b exponential iota omega t minus k z. All the terms we have already explained. Now, in order to find out the solution, that means this is the equation which is given to you. When we say about the solution, that means we are interested to find out modified ground motion when some incident motion characteristics are given to you. Incident motion characteristics means how at your observation point, which may be this particular bedrock condition, what is the ground motion characteristics, how much change in the acceleration value at unit time interval. It can be 0.05 seconds, it can be 0.05 seconds, depending upon the rate at which every time the sensor is detecting the change in displacement velocity or acceleration values, that is going to give me the complete record is basically the ground motion of interest. So, taking that ground motion into account and the medium characteristics which are defined by k value, which is basically important component correlating with the operating frequency and stiffness of the medium, we will try to find out how the motion which has been incident at bedrock level will be changed from the bottom of a given soil layer to the top of the soil layer. So, solution of one dimensional wave equation means finding out the functional form of u. Solution of this particular problem is to find out how much is the modified ground motion will be at the top of the particular given soil medium. Now, omega is the circular frequency, k is the wave number, and a and v are the amplitude of the motions travelling in upward and downward direction. If you compare these with respect to the general equation of motion, as I mentioned, the shear stress for undamped system is directly proportional to shear strain, and that is the only component which is going to offer resistance to external loading condition. So, the shear strain, we have discussed this earlier also, that it can be defined as dou u over dou z. You have the value of u given in this particular equation. So, once that value of u is known to us from this particular equation, we can differentiate partially this equation with respect to z. We will get the value of shear strain. So, this equation which is given, the term which is given inside this particular bracket is basically obtained by differentiating this entire equation with respect to z. That means, this is the value of u differentiating with respect to z, partially you are going to get iota k times a exponential iota omega t plus k z minus iota k times b exponential iota omega t minus k z. So, that is the Guwahati equation correlating the shear strain and a particular medium. Multiply that with respect to the shear modulus of the medium, which is again constant, because we are taking into account it is linear elastic, and we are also dealing with linear ground response analysis. So, you will get the value of shear stress from here. Now, again there are some boundary condition. Remember, in this particular case we are not taking n number of layers available above the bedrock. We are only taking into account that there is a rigid bedrock medium on which incident waves are coming, and above this particular bedrock medium only one layer of undamped soil is available. We are not right now concerned about n number of layers above the bedrock. In practical situation, you often encounter more than one layers available between the bedrock and the surface. So, we will go step by step and we will see how that particular solution can be obtained where number of layers are more than one. In this particular case, there are some boundary condition, that means at free surface. So, only one soil layer is there, below that particular soil layer bedrock is there, and above that particular soil layer it is ground surface, it is free surface. So, when it is free surface, it is not offering any kind of resistance to deformation. So, this particular free surface, that means the ground surface, the shear stress and subsequently the shear strain is 0. That is the boundary condition, that is at free surface, that means at z equals to 0. Remember, z is increasing with respect to depth starting from the top of soil layer. So, it is increasing downward. Apply this particular equation condition to the previous equation, that is equation number 3. 0 will be on right hand side, because this is the value of tau stress free surface. So, this is the value of tau stress free condition on the ground surface. It is free to move, it is not offering resistance. So, 0 equals to the other part. Now, in this, if you see, the entire equation can only be equals to 0 if A is equals to B. That means, the amplitude of downward and upward propagating wave in this particular case are equal. When these two things are equal, you can put this in the Guwahati equation of motion. Using this in equation number 3, you will get, that is the equation which was defining the displacement at any space and time, u z comma t equals to 2 times A, because now A and B are equal. So, I have replaced B by A, 2A, and then the term in the within the bracket exponential iota omega t, and this can be further written as 2A cosine of k z exponential iota omega t, because this term which is given within the bracket can be replaced by means of cosine of k times z. K is wave number, z is the displacement or the position of point of observation starting from the surface of the ground towards in downward direction. So, again we define a function called as, this function is called as transfer function If you remember lecture 17, transfer function was basically used to transfer the motion from the bedrock to the surface, or more precisely from the base of a particular soil layer to the top of that particular soil layer. In this particular case, we are having just single soil layer. So, the transfer function here has been defined as displacement, maximum displacement at the ground surface at some point of time capital T divided by the maximum displacement at the bottom of that particular soil layer, because H is the thickness of that particular soil layer at the same moment of time capital T. That means, at same moment of time when a particular soil layer is subjected to loading condition, how much is the displacement at the surface, how much is the displacement at the bottom, that is basically going to define my transfer function. How you are going to get the values of u x, u at 0 and u at h z equals to h. We have the Guwahati equation which is just derived in the previous equation. So, this equation you can use, which is given over here, determine the value at the top surface, that means z equals to 0 and z equals to h, you will get these values. So, z I have simply replaced by means of h and equals to z also in denominator and numerator. So, the right hand side of this particular equation, equation 6, it is going to define the ratio of displacements at same moment of time between the ground surface or the top of that particular soil layer and bottom of that particular soil layer. In other ways, I am interested to find out how much is the displacement at the top of this particular soil layer will be if I know the displacement at the bottom of that soil layer based on recorded ground motion. So, in actual we will be interested to find out the displacement at the surface, but taking the boundary condition, that is free surface condition, into account, I have defined a filter which can be used to transfer my motion, recorded motion, from the bottom to the top of the particular soil layer. So, this is, if you see the right hand side of the equation, everything is given in terms of 1 over cos cosine of wave number multiplied by the thickness of the soil layer, because other terms will get cancelled out. So, rest of the things will get cancelled out. Cos 0 is 1 over cosine of k times h, that is going to define my transfer function, which is given over here. Now, this is the transfer function which is going to tell me how much modification is there between the bedrock and the surface. And remember, the value of k, which is given in equation number 7, is basically the ratio of operating frequency in radian per second divided by the shear wave velocity of the medium of interest. So, using this particular ratio omega over Vs, I can define how much is the value of wave number. Once that wave number is known to you, or you can directly put the value of k equals to Vs over V over omega over Vs times h in this particular equation, you will be able to determine. See, here we did not require any value of time, we need not require any value of intermediate thickness, simply what we require is the value of h. That means, when we are going with linear ground response analysis, we are also assuming that one particular soil layer, whatever is the thickness of that particular soil layer, at any moment of time, the soil layer will remain constant. So, any kind of motion within the particular soil layer, it is not going to change significantly within that, it is going to remain constant. So, Vs over omega over Vs, it is basically defining the value of wave number, and based on the previous understanding, we are telling like throughout at any moment of time the entire layer is going to respond as same. So, the modulus of the transfer function, that means this modulus is going to give us how much is the amplification between the bedrock and the surface. It is also notable that the surface displacement, based on this particular equation, the maximum value can be anything if the denominator of f omega, that is transfer function, if the denominator becomes 0, that transfer function becomes very high. In such a case, the soil medium will experience resonance. That means, whatever is the input motion, the surface motion will be remarkably high, and anything which is less than 0, that means the maximum value of the denominator can be 1. In such a case, the transfer function value itself will be 1, or there will not be change in motion properties between the base and the top of the particular soil layer. So, that means it says that the maximum value of the transfer function can be as high as infinity, minimum value should be at least 1 for the transfer function based on the equation given over here, because h will always have some value, wave number will always be there. So, the minimum value of transfer function can be, you can get a value of 1, maximum value of transfer function can be as high as infinity. So, keep on changing the value of omega, because Vs value is going to remain constant, keep on changing the value of omega 0, pi by 4, 3 pi by 4, pi, and so on and so forth, and every time you put the value over here, you will get the value of transfer function. Always keep in mind the value of omega you are going to use, it is in radians per second. So, if you use those things over here, you are going to define the variation in transfer function. This is going to give you the mode of transfer function f omega, which is defined in the equation 6 in the previous slide. You keep on changing the value of k h, or most precisely the value of omega, because h and Vs are not going to change. So, only value of omega you are going to change over here. You see over here, when the value of k h becomes pi by 2, the value of transfer function becomes infinity. That means, at omega corresponding value where kh equals to pi by 2, your system is experiencing resonance, and this characteristics of resonance is getting repeated at every pi interval. So, I can say here any value of n pi by 2 plus pi, this value is getting repeated. That means, pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, 9 pi by 2. Every time when the value of kh reaches these values, the transfer function becomes infinite, and in between this is having some finite value, and the minimum value of transfer function is 1. So, it is not possible to have any value of transfer function lesser than 1. Now, in order to understand this particular problem more specifically, we will try to solve a numerical. So, what we are trying to understand here is, if there is a rigid rock on which incident ground motion is available, that means bedrock motion beneath the soil layer is available, and above that particular motion, above that particular bedrock, there is undamped soil of thickness capital H available. How this particular soil layer of thickness H is going to experience change in motion characteristics between the bottom to the surface of that particular soil layer. So, what we tried determining? We tried finding out the value of displacements at the free surface and at the bottom of that particular soil layer, and the ratio of these two displacements I am defining as the transfer function. So, this transfer function is going to basically tell me how the displacement is going to change between the bottom and the top of that particular soil layer of interest. And once we know this value of transfer function, we have seen the minimum value of transfer function is 1 and the maximum value of transfer function is infinity. Infinity means it is indicating the resonance. So, how to solve the equation? Because this is, so far we are doing the derivation part, we have not taken any ground motion into account, we have not taken any specific soil layer into account. So, in order to demonstrate how the methodology which we have just now discussed, it is a part of linear ground response analysis, that too medium is undamped, rock is rigid. So, here is the example. For a site having average shear velocity of 340 meter per second, compute acceleration time history or time history of acceleration at the surface of the soil layer having 4 meter thickness and overlying a rigid bedrock, considering that a deposit for undamped condition. That means, the soil layer is firstly linear elastic having thickness H, capital H equals to 4 meter, and it is located above rigid bedrock. So, we are interested to find out if there is a motion given to you, and it is also defined that the rigid the bedrock is rigid, how much amplification in this motion will happen because of 4 meter of soil layer which is linear elastic undamped soil. How we are going to solve it? First of all, write down what is given to you. The problem, again, one thing which was not defined here is which motion one has to take into account. So, either you can be given the motion or you can adopt some motion and just say like I am going to perform ground response analysis considering a particular motion. So, as far as motion selection is concerned, you can go with seismic hazard analysis, find out what is the expected level of bedrock motion or site class A motion expected at your site of interest, corresponding to that value of P ground acceleration or PGA, select a motion from a region which is having comparable seismic activity or generate synthetic ground motion, or if regional ground motion record is there, you take that into account. If none of these are there, and if you are doing ground response analysis, then you have to be very precise that I have done ground response analysis considering this particular motion. Generally, people use Loma Prieta earthquake, Bhuj earthquake, Sikkim earthquake, Nepal earthquake, Chaukan earthquake, Chile earthquake. So, one has to refer which particular earthquake and the year in which the earthquake has happened, because not every place earthquake happens just once. So, wherever earthquakes are very frequently, people can get confused which year earthquake one is referring to. So, every time you are mentioning about earthquake, also mention which is the year in which the earthquake has happened. So, in this particular case, I am referring to another earthquake which has happened in 1985 in Chile. The peak ground acceleration of that particular earthquake, that means corresponding to acceleration time history record, the peak value after all the corrections, whatever is the peak value of acceleration, that is called as peak ground acceleration. So, that value is given as 0.12 g. Now, in order to solve this, as I mentioned earlier, you can take any motion into account. The steps to be followed remain the same. Only thing, depending upon the motion characteristics, your value of omega will change, and subsequently your value of Fourier spectra at the bedrock will change. So, any motion one can use. Firstly, one has to do Fourier transformation, because the record for Chile earthquake or any other earthquake will be given in terms of acceleration time history or velocity or displacement time history. So, we have to find out the Fourier spectra, which can be done using fast Fourier transformation. You can use different tools to do fast Fourier transformation. Here I will be using Excel tool to determine how the fast Fourier transformation will be done. So, to do that, ensure that Microsoft Excel has activated data analysis. So, if you go to data analysis option, you have to actually activate that, then only this particular option for Fourier transformation you can use. So, again, when we go for fast Fourier transformation, a maximum number of data points are limited to 4096 in your acceleration time history record. So, the procedure for computing ground response analysis for linear elastic undamped soil located over a rigid half space. So, what we will do? The procedure remains same, but the Guwahati equation will change. If you move from undamped to damped soil, if you move from elastic to rigid to elastic half space, the procedure will remain same. The generation of Fourier series at bedrock level, that means whatever recorded motions are there, those have to be converted from time domain to frequency domain using fast Fourier transformation or Fourier analysis. So, here you can go with data analysis and then Fourier analysis in Excel. Whatever input motions are there in terms of acceleration values, you can give, it will give you the amplitude, and based on the frequency of time recording during your earthquake, that is going to define how much is the maximum and minimum frequency content available in your particular motion. So, the result corresponding to initial 10 points of acceleration are basically shown over here. So, firstly your ground motion records you will convert from acceleration time history to Fourier spectra using data. You go to data and then data analysis and then Fourier analysis. You can see over here, once you go to Fourier analysis, it is going to tell you how much is the input range. So, here in order to decide about the amplitude of motion, you will take into account the column in which. So, this is the column where basically your ground motion record was having acceleration versus time record. Often you will be given the value of acceleration, the unit of that, and the frequency or the time interval in which each value of acceleration has been recorded or sensed by the sensor. If it is given, this is the value of acceleration recorded at 0.005 seconds, that means at every 0.005 increment, next value of acceleration has been recorded by your recording station. So, put all those values of time at an interval of 0.005 seconds interval or whatever has been given by your recording station or corresponding agency, that will be there in first column. The measured value of acceleration will be there in second column. Now, here when you go for Fourier analysis, you have to basically tell what is the range of your acceleration values, because your amplitude you will be getting from there. So, it is given over here, this is column A, this is column B and this is column C. Then output range, that means the Fourier amplitude, you have to also define where the Fourier amplitude has to be put. As I mentioned, maximum number of points you can give as 4096. So, it is starting from second row and going up to 4097, that means the total number of data points which you can use it is 4096, and the output of Fourier amplitude you are going to put in terms of column C. Now, in order to find out the frequency content, we know that each point has been recorded at an interval of 0.005 seconds. So, based on that you can find out how much is the highest frequency of the motion, that is 1 over delta t. Delta t is the time interval within which each value of acceleration is recorded. For this particular record, it is given as 0.005 seconds. So, 1 over 0.005, that is 200 hertz, is the highest frequency which is available in your record, acceleration time history record, if you talk in terms of frequency domain. Now, the minimum frequencies, you know, 4096 points are there, recorded at 0.005 second interval. So, product of these two is going to tell you the duration, 1 over the duration, it is going to give you how much the minimum frequency available in your record. Frequency interval or successive frequency which will be known to you is the first frequency f1 plus the time interval into total number of data points and inverse of that. So, f1 plus 1 over 0.005 into 4096, it is going to give you the successive interval of frequency. So, f1, f2 and then up to 200 hertz. If you say in terms of the amplitude, whatever motion you are getting up to an request frequency, that motion in rest half cycle, that means if it is having the highest frequency of 200 hertz. So, from 0 to 100 hertz the amplitude of the motion you can find out, but from 100 to 200 hertz it will be the conjugate of the motion which is available from 0 to 100, which can be evidenced from this particular plot also. You can see over here the frequency, the amplitude of the motion from 0 to 100, it is coming like this as shown over here. So, in last column you can see up to 100, this is the amplitude of the motion, but after 100 if you go to the next motion, it is basically getting repeated over here. So, you can see this particular motion is getting repeated over here, this motion is getting repeated over here, this motion is getting repeated over here, and subsequently. So, it is like the cycle is getting repeated after 100 hertz, which is an equus frequency which has been indicated by the recording frequency. So, this motion, that means the amplitude of the motion is getting conjugate. Now, the generation of transfer function, that means f omega value, f omega was cosine of 1 over cosine of k times h, k is wave number, h is the thickness of the soil layer, which in this particular case is given as 4 meter. So, this is already defined, omega value, h value is the thickness and Vs is 340 meter per second, which is given in this particular solution. Omega is the circular frequency content of the motion, which can be defined now. Just now we have defined the frequency content of the motion, multiply by 2 pi. So, omega will be equals to 2 pi f, f frequency content you have defined, multiply by 2 times pi into the frequency content, you will get circular frequency or frequency in radian per second. H is the thickness given in 4 meter, shear velocity of the medium is given as 340 meter per second. So, number of data points again will be considered as same to that of how many number of points were there in frequency content, that is up to 100 hertz. Again in next slide only the frequency, the transfer function values for first 10 terms, corresponding to which the acceleration values and later on the Fourier amplitude values are also given. So, in next slide we will be also getting the transfer function, and mode of the transfer function is going to give you how much the amplification function. So, this is the frequency content, first 10 frequency content, and corresponding to that the transfer function values. The Fourier spectra of the ground surface as discussed in lecture 17 and here also in the beginning. So, when we are interested to find out the Fourier spectra at the ground surface, you have to take the Fourier spectra at the bottom of that particular soil layer, multiply by the transfer function that is going to give you the Fourier spectra at the surface. So, f a is going to tell you how much is amplitude multiplied by the transfer function at each frequency content. The amplitude is also known at each frequency content, and corresponding to that frequency you have the value of omega. Put the value of omega, you try to determine the value of transfer function. So, both the Fourier amplitude as well as f omega or transfer function, both are the function of the frequency content of the motion. Multiplication of these two values, you can determine how much will be the Fourier amplitude at the ground surface. Only thing, there will be complex quantities also. So, that you can use imprompt function and it will give you the compatible inbuilt real values. So, Fourier series from 100 to 200 hertz basically will have conjugate components of 0 to 100 hertz. The frequencies, the Fourier series from 0 to 100 to 200 hertz will be a conjugate complex of the values which are available from 0 to 100 hertz. So, again using IM conjugate you can basically find out what is the Fourier amplitude at the ground surface corresponding to 100 to 200, which can be put over here either manually or using IM conjugate. So, you can see over here 100 to up to 100 hertz, what are the values there? Once you go to 101, the value is getting repeated, and the value which is given on the first is getting repeated in the fourth column. So, that is how you keep on repeating. So, it is like up to 100 hertz values are there, and after 100 hertz similar to Fourier amplitude, because this is also going to give you Fourier amplitude at the ground surface, that will be also conjugate value of from 0 to 100. Now, you based on this process you have determined the Fourier amplitude at the ground surface, which now has to be transferred from frequency domain to time domain. So, if you remember, the actually ground motion was given in terms of acceleration time history at the base of the soil column. Now, you based on this product of Fourier spectra and the transfer function, Fourier amplitude or transfer function, that is going to give you acceleration Fourier spectra at the ground surface, which has to be converted to acceleration time history. So, that can be done again using inverse fast Fourier transformation. You can go to data science analysis, and then Fourier analysis. Then there you can provide the input, that is Fourier amplitude at the ground surface, and choose inverse which is given in the options there, that is going to, and press OK. It is going to give you the acceleration time history values. So, here you can see you are basically selecting how much is the input value, that means how much is the Fourier amplitude at the ground surface, and then check inverse. It is going to do inverse fast Fourier transformation and give you the value in time domain, that is acceleration time history values at the ground surface. So, you started the acceleration time history at the bottom, converted to fast Fourier transformation and converted that to Fourier spectra or frequency domain, multiply this value with respect to the transfer function, which was again based on the operating frequency converted to circular frequency, thickness of the soil layer and shear velocity of the medium. Estimate the transfer function, take the amplitude of the transfer function, multiply with the successive value of Fourier amplitude at the same frequency, you will get the Fourier spectra at the ground surface. Then performing inverse fast Fourier transformation, you will be able to convert this from frequency domain to time domain, and subsequently this is going to give you the acceleration time history at the ground surface. So, some typical outputs which are given over here are bedrock acceleration versus time, which was the input which was taken from 1985 Chile earthquake, then 4-year plot of that particular motion, then amplification versus frequency content or the transfer function values over the entire frequency range, then Fourier amplitude at the ground surface, and then acceleration time history at the ground surface. So, all these plots or the processes which have been done have been also shown in terms of these plots, which is given over here. So, this is bedrock corresponding acceleration time history, which has been taken in this particular example, converted to frequency domain using Fourier spectra, Fourier analysis, which is discussed in the previous slides. From here you determine amplitude versus frequency content. This is the transfer function variation over the frequencies of interest. This is again acceleration time history at the ground surface, which was given based on the product of transfer function and Fourier amplitude at the bedrock, which is going to give you the Fourier amplitude at the surface and converting it from time domain to frequency domain to time domain. This is the acceleration time history at the surface. So, that is how one can quantify how much change in the, if you are able to compare this particular motion which is available at the ground surface with respect to the motion which is available at the bedrock, you yourself can compare and see that because of local soil there is significant change in the motion characteristics. But only thing, remember that this is corresponding to linear undamped soil. In reality there will be damped soil and there will be elastic half space also. So, this is one simplest example which has been taken to demonstrate how one can perform local side effect or ground response analysis using linear approach. So, thank you. With this we close this particular topic of undamped soil located over a rigid half space. We will try to solve one or two more examples related to damped soil over rigid half space and elastic half space, and then we will move to other methods. Thank you everyone.